Okay, today we're talking about conservation of momentum a little bit further. As part of this, we will clarify some of the things that we should have done yesterday during the lab and go over those answers so you can make sure that you have everything ready for your lab quiz on Thursday. And we will also expand that information a little bit further and do some practice. Okay. The key thing to write down here is that momentum is conserved in a closed, isolated system. Mass remains constant. That's what determines that it's closed. And this would be the mass of one object plus the mass of the other. That mass is the total mass of the system, and it would remain constant. And there'd be no external forces acting on the system, which is what would make it isolated. You don't need to write all of this down, but just the key thing here is that there's no mass transfer. The mass of our objects is going to stay the same. And there may be energy in and energy out, but there's still a closed system. There's no external forces acting on the system. Okay, when a system is open, the mass of the system itself can change. The main thing is just to know that momentum is not always conserved, and the real world tends to act in such a way that momentum is not conserved. So this is a real world application. Okay, and this is because you've got objects that are interacting with objects in the surrounding environment. And because we're surrounded by air and we have friction on the ground, there's always going to be something that is essentially going to take the velocity component of momentum out of momentum. Okay, so the law of conservation of momentum very basically says if conservation is occurring, then momentum lost by one object in a system must equal the gain of the other object in the system. So we have our formula here, which was on your lab yesterday and on your lab instructions yesterday, and which we also had encountered last week. And essentially, it's just that the initial momentum has to equal the final momentum. So our initial has to equal the final momentum. Because we have two objects, we have to add the momentum of object 1 plus the momentum of object 2 before they interact. That's going to equal the total momentum of the system. So object 1 plus object 2's momentum, so we might say the momentum of object 1 plus the momentum of object 2 is always going to equal the total momentum of the system. And that total momentum has to equal the momentum of object 1 after, so that's the momentum of 1 final, plus the momentum of object 2 final. So very simply, the thing that might change is the objects. It's just right here. So we have an initial velocity here and here, and what is going to potentially change is the final velocity for both of our objects, for one or both of our objects. And if one changes, then the other must change because their masses cannot change. So another way to look at this is to say the sum of the momentums for our two objects before the interaction is equal to the total momentum and is equal to the sum of the momentums after the interaction. And again, this is when we have a closed system. Okay, so this is what we had yesterday when we were doing the PhET. So this is with the elastic collisions, and the key here was this. It sort of was that you had to first look at doing everything on the left side of this line before you could do the after collision part. And essentially what you needed to do is recognize that you were given information for two objects. You had here the mass of object 1 and the initial velocity for object 1. So you would add those together. And then you have the mass of object 2 and the velocity, the initial velocity of object 2. Okay, and you would multiply those two things together. I think a moment ago I misspoke. What I highlighted in yellow, m1 and v1i, we would multiply those together. Our product would be the momentum of object 1, and the pink highlighted mass 2 times velocity 2 initial would give us the momentum of object 2. The sum of those momentums before a collision has to equal the sum of those momentums after the collision. But here's the key right here, our total momentum. The momentum before has to equal the momentum after, has to equal the total momentum. So for our first one, we have a total momentum of 0 kilograms times meters per second. So that means that the momentum of object 1, oops, let me switch back to this. And so the momentum of object 1 initial plus the momentum of object 2 initial, in this case, has to equal 0. And remember, momentum is always mass times velocity for our objects. So for object 1, it's going to be the mass of 1 times the velocity of 1 initially. And in this case, we have, for object 1, 2 kilograms and 1.5 meters per second. So for object 1, we get a momentum of 2 times 1.5, which is 3 kilograms times meters per second. Now that plus our other momentum of the other object has to equal 0. So what plus 3 will equal 0? That would be negative 3 kilograms meters per second. So we need this right here to be a number that when multiplied with 2 kilograms will give us negative 3 kilograms meters per second. So just like 1.5 meters per second times 2 kilograms gives us positive 3, negative 1.5 meters per second times 2 kilograms will give us negative 3 kilograms meters per second. So now we have our 0 kilograms times meters per second. Then what you needed to do was run the simulation for the first object and then record their after collision velocities. I'm going to go ahead and clear the screen because it's looking a little messy, and then I'm going to rewrite in here the negative 1.5 kilograms meters per second. Okay, and when you run the collision, then after they bounced and you paused it, then you would get their final velocities. And what we see for object 1 is that where it was positive 1.5 meters per second before the collision, it's now negative 1.5 meters per second after the collision, and object 2's velocity after colliding is positive 1.5 meters per second. Now these objects have the same mass. Their velocities were of the same value, although in opposite directions, and that stayed the same after colliding, although they went off in opposite directions at that point. Okay, so for number 2, again, we have a total momentum that is equal to 0. So we need to see what the momentum of our second object is in this case, because this time we're given V2 and M2, whereas we're missing right here V1I. So we have to figure out what times 2.5 kilograms will equal 5 times negative 1 meters per second in terms of momentum. So 5 times negative 1 meters per second is going to equal, so I'm doing this times this. That's going to give me a momentum for object 2 of negative 5 kilograms meters per second. And since I need to equal 0 kilograms meters per second, then I know that momentum 1 has to equal positive 5 kilograms meters per second. So now I'm looking at this times what, right here, will give me positive 5 kilograms meters per second. So 2.5 times 2 meters per second. That's not a very good color, is it? So 2 meters per second is going to give me my positive 5 kilograms meters per second, and positive 5 plus negative 5 will give me my 0 right here. So then again, I'm going to erase this just to clear it up. This was negative, and well, the u should already have that, so I'm not going to worry about that. So we just determined that this should be 2 meters per second. So after the collision, when you run this, you see that you get a final velocity of negative 2 meters per second for the first object and 1 meter per second for the second object. So in this case, they retained their value of velocities, but they changed their direction. Before object 1 was 2 meters per second, after it's negative 2 meters per second. So we should start to see sort of a pattern that's developing that might help us think about what happens in elastic collisions in terms of velocity. Now, it's going to change a little bit here with number 3, because now we're dealing with a situation where we've got very different momentums, and we have a momentum that is not equal to 0 in this case. So we have to figure out a momentum. So first what we want to do is take the 3 kilograms for object 1, and it's 2 meters per second. And so then for momentum of object 1, we get a bad color again. Let's do this one. Okay, so we get a momentum for object 1 that's equal to the 3 times the 2, which is 6 kilograms meters per second. And the momentum of object 2 is going to be the 6 kilograms times the 0 meters per second. And of course, 6 times 0 is going to be 0 kilograms times meters per second. So the momentum of the second object is none. It's stationary. But the total momentum then is going to be 6 plus 0, or 6 kilograms meters per second. Okay, so then we run the simulation and we see what the velocities are after, and we get something different this time. So we get negative 0.67 meters per second, and we get positive for the second object 1.33 meters per second. Okay, so now if we looked at that, the final velocity for object 1 times its mass plus the final velocity for object 2 times its mass is still going to add up to a total momentum of 6 kilograms times meters per second. But notice here that because we have different masses in our objects, we end up with both of them moving, okay, and the first object changes direction. How do I know it changes direction? It was positive here, and now it's negative over here. So it has changed direction and bounced off. This went from being stationary, so that's sort of neutral, to moving to the right at 1.33 meters per second. Notice how if we subtracted one of these velocities from the other, if we did 1.33 minus negative 0.67, that would add up to 2 meters per second. So that's something that you might want to look at as we continue along in our elastic collisions momentums. Okay, so now with the very last one, our total momentum is 8 kilograms times meters per second. So our two momentums before the collision have to add up to 8 kilograms times meters per second. And we're given the information for object 1 that allows us to calculate the momentum of object 1, which is going to be 6 kilograms times 2 meters per second, or 12 kilograms times meters per second. So what we find then is that our second object's momentum needs to equal negative 4 kilograms times meters per second, because 12 plus negative 4 gives me my 8 kilograms times meters per second. So when I look at what I have for the second object, I have a velocity of negative 1. So, of course, 4 kilograms times negative 1 will give me this negative 4 kilograms meters per second that I need for a total momentum of 8 kilograms times meters per second. So then you run the simulation and you record the velocity of the objects after they have collided, and you pause the simulation to see what you get, and you should have gotten negative 0.4 meters per second. And for object 2, you should have gotten 2.6 meters per second. Okay, and so what you see here again is a change in direction. Object 1 was moving to the right. After the collision, it's moving to the left, and object 2 before the collision was moving to the left, and after the collision is moving to the right with the greater velocity. So notice that it has less mass, object 2, and then it gains more velocity than it had to begin with. Because they don't have, well, anyway, just look at the pattern that you see with these numbers, and let's go ahead and fill them all in so we can kind of look at what happened when masses were the same and when they were different and so on. I'm going to go ahead and erase all that and then finish recording everything. So negative 0.67 meters per second. That's a 0. And 1.33 meters per second. And then this was negative 1.5 meters per second. This was 2 meters per second. And this was 6 kilograms times meters per second. Okay, so what we see here then is this pattern. So for the first one, we have identical masses. We have identical magnitude of velocities, although in opposite directions. And because of the identical masses and identical magnitude of velocities, the magnitude of velocity for each stays the same afterwards as well. For the second object, the mass of the second object is, for the second collision, the mass of the second object, so here, for the second collision, the mass of object 2 is twice that of the mass of object 1. So we also see that they have different magnitudes of velocity. So what we see happen with these is we see that object 1 maintains its magnitude of velocity, but it changes direction, and same thing with object 2, even though the masses are different. And that's because really they had equal but opposite momentum, so each had to maintain its own momentum. So for our first two situations, they had equal but opposite momentums, so they had to maintain their equal but opposite momentums. If their mass didn't change, then their velocity also needs to not change in magnitude, only in direction. Okay, for the second two scenarios, we actually have some different things happen because they do not have equal but opposite momentums. The momentum of object 1 compared to the momentum of object 2 before they collide is different. And the momentum of object 1 compared to its momentum after the collision is also different. The total of the two momentums before and the two momentums after does still have to be the same. So that is why we see the type of changes that we see with these elastic collisions. Okay, so let's talk a little bit further about elastic collisions here. So in elastic collisions, the total momentum and the total kinetic energy of a system is conserved. And this is the key thing that we're really adding to our information about momentum and conservation. The total kinetic energy, whoops, let me go back. The total kinetic energy of elastic systems is conserved. The objects bounce off of each other, and if one has a greater kinetic energy than the other, it will transfer some or all of its kinetic energy to the other object, and that causes a change in momentum for each object, potentially. Okay, so let's look at an example where we see this. Okay, and so here we have a little animation that It's going to be a bit challenging for me to start the way I have this set up right now. But in any case, we'll play that in just a second. So, but first let's look at what we have. So we have train car 1. It has a mass of 1 kilogram and a velocity of 2 meters per second. And we have train car 2 in green, and it has a mass of 1 kilogram, so their masses are equal, and it has no velocity. And notice how the button for lock cars is not clicked, so it's going to have an elastic collision. It's going to bounce off. And so it also tells us right here our momentum before the impact and of train 1 plus train 2. So here's train 1 plus train 2. And it tells us the momentum after impact, which, let's play this and see what happens, because I don't think that's the way it's supposed to stay. Okay, I see what happens. Before we play the animation, there is no momentum after impact because there hasn't been an impact yet. So this is why. So when we play the animation, we'll see what happens. Okay, so here our cars collide. Let's pause it for a second. And so now we see that the momentum before the impact equals the momentum after the impact, as it should. Okay. But you'll notice that the momentum shifted. If we look at that one more time, the momentum shifted from the blue to the green train car. The blue becomes stationary and the green moves off with all of the momentum. So there's been a transfer of momentum from the blue train car, which had all of the momentum of the system before the collision. It transfers it to the green car, and then after the collision, all of the momentum of the system is now contained in the green car. And it played one more time just for fun. Okay, so now let's go on to our next slide. Okay, so let's practice a problem. We have a blue train car with a mass of 1 kilogram and a velocity of 2 meters per second that collides elastically with a stationary green train car with a mass of 1 kilogram. And this is asking, what is the velocity of the green train car after the collision? Okay, so this actually should not be a terribly complicated problem. When we set this up, first of all, we know that the M1 V1 is going to be equal to M2 V2 because the momentum of the moving car right here is going to transfer to the stationary car. Whenever you have an elastic collision where one object is stationary and the other collides with it, then you'll see that the one that was moving will sometimes come to a stop, and that's going to be the case here. So this is written a bit strangely, not anyway. Maybe perhaps not exactly how I would have described it. Okay. All right. So let me go back to that problem for just a second and kind of go through it a little bit better. Let's get rid of the way that it's explained here. Essentially, in this case, because they have the same masses. Okay, so the blue train car and the green train car have the same mass. That means that we can kind of factor the mass out because the momentum before is all in the blue train car. This is basically what we just saw. So the velocity of 2 meters per second is going to transfer from blue to the green train car. So the blue had 2 meters per second before the collision, so all of that will get transferred to the green train car because they have the same mass. Okay, the next problem here, this one, is a little bit more like the kinds of problems that you're going to see with conservation of momentum in elastic collisions, where we have a blue train car that has a mass of 1 kilogram and a velocity of 2 meters per second, and it's going to collide elastically with a green train car that has a velocity of 1 meter per second. And notice that both of these are positive velocities, as they're meant to be. So we're going to look at this animation here, okay? And if we had done the calculations before, we would have seen basically what happens in the momentum before impact. It's telling you it's 3 kilograms times meters per second. That means that the total momentum after impact has to be the same thing. Before the impact happens, it's saying that it's 0 because we have to play the animation to see what happens. So as it starts here, the blue train car catches up with, blue train car catches up with the green train car, hits it, and transfers some of its momentum to it. So now we see that the momentum before the impact does equal the momentum after the impact for both of them. And notice that, let's look at that one more time, notice that when the blue train car hits, what happens to its momentum? It actually changes. Before the collision, the blue train car was 1 kilogram times 2 meters per second. After the collision, the blue train car is 1 kilogram times 1 meter per second. The green train car had 1 kilogram and 1 meter per second, and then after the collision, it's 1 kilogram and 2 meters per second. Okay, so we have a transfer of momentum from the blue to the green train car. However, the total momentum does stay the same. It's 3 kilograms before, it's 3 kilograms after. Although now the green train car carries more of the momentum than it had before the collision. Okay. All right. Now, how do we go about looking at that mathematically in the way that we do it here? So we've got a blue train car with a mass of 1 kilogram and a velocity of 2 meters per second. This is exactly the scenario that we just had. So we want to see what happens. How would we calculate the velocity of the green train car after the collision? On this previous slide, it just gave you the velocity, but if I asked you on the test or the quiz and you needed to calculate it, then you would need to use this formula. And remember, this formula looks more scary than it really is. It's just saying that the momentum of the first object plus the momentum of the second object before they collide has to equal the momentum of the first object plus the momentum of the second object after they collide. So the individual values for the first object, the velocity value may change, but that means that there has to then be a change in the velocity of the second object in order to compensate. So the momentum that one loses, the other must gain an equal amount of momentum. So taking a look at that, continuing on, okay, we substitute in the numbers that we know for these values. So we've got 1 kilogram right here for M1, and we've got 2 meters per second for the velocity of the blue train car initially, and then we have 1 kilogram for the mass of the green train car, and it's initially traveling 1 meter per second before it collides. On a side note, this is a good example also of an elastic collision. They're not always moving towards each other. If one is going faster than the other, it can catch up to it and then hit it, and they still collide elastically, and this is a good example that shows that. All right, so then moving on. So it tells you that after the collision, the mass of the blue train car, of course, stays the same, but its velocity is now 1 kilogram meters per second. The mass of the green train car has stayed the same, and so now we're left with our value that we're trying to find, which is V2F. So continuing on, okay, when we simplify on both sides, 1 times 2 is 2, plus 1 times 1, which is 1, gives us 3. On the other side, we have 1 times 1, which is 1, and then 1 times V2F is just V2, and the F got dropped off of the subscript there for V2, but in any case, we're solving for the final velocity of the second object after the collision. So then when we further simplify, we need to subtract 1 from both sides. And so when we do that, we get 2 meters per second for the final velocity of the green train car, or the second object. Okay, so now we're going to go over the inelastic collision section of the PhET. And in a sense, this one was fairly more straightforward when we were looking at what's happening. So because you're given the masses of both objects and the velocities of both objects, so you have to calculate the initial velocity times mass for object 1 and the initial velocity for object 2 times its mass. So for object 1, we have 2 kilograms times 1.5 meters per second, and that gives us, I'm going to just jot it right in here, it gives us a momentum that's equal to 3 kilograms meters per second. Now because the velocity of object 2 is 0, its momentum is going to be 0 kilograms meters per second. So that means that our total momentum is 3 kilograms meters per second plus 0, or just 3 kilograms times meters per second. Okay, now there's no way, well, we could actually calculate the after collision velocity. The reason that this column heading says V1 and V2 is because in an inelastic collision, those things are stuck together, and so they will be moving with the same velocity. If two things are stuck together, one cannot be going faster than the other, or they don't stay stuck together. All right, so when we do run the collision, we see that afterwards the velocity that they have is 0.75 meters per second. That's the velocity of both of them. So if we look at checking that with math, basically we would see now we have a total mass of 2 plus 2 or 4. So we'd have 4 kilograms times 0.75 meters per second, and 4 times 0.75 does indeed equal 3 kilograms times meters per second. So we see that our momentum has been conserved in this case. Okay, for the next one, we have 3 for M1 times 1.5 for V1, and 3 times 1.5 is going to give us 4.5 kilograms meters per second, so that's our P. And for the second object in this case, it's going to be 6 times negative 0.75, so that actually equals negative 4.5 kilograms times meters per second. I'm sorry, that's so messy. But 4.5 plus negative 4.5 gives us 0 kilograms times meters per second for our total momentum. And does that mean nothing's happening? No, of course, that's the total momentum. Each object has a momentum. They're moving towards each other and they collide. When they do collide, after the collision, they are going to have no velocity. They hit and come to a standstill. And this is because they had equal but opposite momentums, and it's an inelastic collision. Now, if this was an elastic collision, they would have hit, bounced off in opposite directions, and they would have retained their velocities. But this is inelastic, so kinetic energy is not conserved in inelastic collisions. All right, so continuing on, for number 3, we have 1.5 times 2, which is going to be 3 kilograms meters per second, and then we have 5 times 0.2, which gives us 1 kilogram times meters per second. So our total momentum is 4 kilograms times meters per second. When we run the PhET, we get 0.62 meters per second for the velocity of both objects after they've collided and stuck together. Okay, for the last one, we're given our total momentum again, so we have to figure out our unknown mass for object 2. When we look at the momentum for object 1, it's this 10 kilograms times 2 meters per second, and so that's going to give us a momentum that's equal to 20 kilograms times meters per second. So in order to equal 10, we need the momentum of object 2 to be a total of negative 10 kilograms times meters per second. So that 20 plus negative 10 gives us 10. So our velocity is negative 1, and of course, having 10 kilograms times -1, that will give us our -10 kilograms meters per second that we need. When we run the simulation, we see that we have an after collision velocity of 0.5 meters per second. Okay, so now let's take a look at how we might do this mathematically. Okay. All right. So first of all, let's keep in mind that I just mentioned something. When we have inelastic collisions, okay, the total momentum of the system is conserved, but kinetic energy converts to other kinds of energy. So the key difference between elastic and inelastic is that in elastic, kinetic energy is conserved. In inelastic, it is not conserved. Okay. Also, it's a hallmark that the objects stick together. Because they stick together, we write our equation for inelastic collisions a little bit differently, where we have the side on the left for the initial condition before the collision still looks very much the same. But after we have M1, whoops, sorry, we have M1 plus M2 times a final velocity. Because they stick together, we can consider their masses as one object. And again, that final velocity has to be the same because they're stuck together and one can't be moving at a different velocity than the other. And the problem that we're looking at here, okay, before the collision, we have our object 1 is moving with 4 kilograms of mass and 6.0 meters per second. So our momentum for our red object right here would be equal to 6 times 4, 24 kilograms times meters per second. The momentum of object 2 moving towards it, it has less mass and less velocity, so it has 2 times -4, or a momentum of -8 kilograms times meters per second. Okay, so if we look at M1 V1I plus M2 V2I, we have 24 plus -8 on this side. Now, adding our two masses together, 4 plus 2 kilograms, for this value right here, gives us 6 kilograms times, and that says that for us right there after the collision, times our velocity. So now this is a matter of solving for V. So when we look at this, I'm just going to erase so it doesn't look quite so messy. Okay, so now we have 24 plus -8 is going to be 16 is equal to 6V. So we divide both sides by 6, and 16 divided by 6 gives us a final velocity of 2.67 meters per second with rounding. Okay, so here we have a car and a truck that stick together in a head-on collision and move. Okay, and you notice that the truck ends up pushing the car in the same direction in which the truck was originally moving, and that's because before the collision, let's see if I can pause this right here. Okay, so before the collision, when we look at the momentum of the car, it is 20,000 kilograms meters per second, and the momentum of the truck in magnitude is greater, 60,000 kilograms meters per second in magnitude, just negative because it's going to the left. So if we look at their total momentum, the total momentum would be the 20,000 plus negative 60,000, or a total momentum between these two things of negative 40,000 kilograms times meters per second. And that means that after they collide, the total still needs to be 40,000 kilograms times meters per second. So let's let it run and then pause it after they've collided. Okay, let's let it go a little bit more. Okay, so they've collided, they've moved off a little bit. And so now we see that there's been a momentum change for both of them. Their velocities have changed, and of course, the velocity is now the same for both of them because they're stuck together. And then the momentum of the first one, -10, of the car, -10,000 kilograms meters per second, plus the momentum of the second one, -30 kilograms meters per second, does indeed still come out to a total of -40,000 kilograms meters per second. Okay. Now, has the kinetic energy changed? Yes, because their velocities have changed. So there's been a loss of kinetic energy into other forms of energy and into dissipated energy by the crumpling of the car and the sound and friction happening between them. But the momentum is still conserved. So in momentum is going to be conserved whether it's elastic or inelastic. But the kinetic energy of inelastic collisions is not conserved. Okay. All right, so here's another inelastic example with the car. Okay, so now in this case, our cars do stick together. So let's run the animation here and see what happens. Oh, and it's time for class, so we'll stop right here.